Hello everyone. In this session, I want to solve two more examples for the application of Bernoulli equation, and then I want to introduce slice gate and crested weir, and after that, this chapter will be finished. Okay, so let's solve another example. So here we have this hose, and we want to determine the flow rate and the pressure in the hose. Okay, so here we have a gauge pressure of P1, which equals to 3 kilopascal. We have air that goes out of this hose, and then this subsection which has a diameter of 0.03 meters, and then this subsection of that hose that has the diameter of 0.01 meter, and then the temperature of air is 15 degrees Celsius. Okay, so and we have air here. So let's see how we can, and now we want to find the pressure in the hose, right? And also I want to find the flow rate and pressure in the hose. So I want to see what is the pressure here, like P2, okay? And also the Q here, which we want to find. Okay, so let's get started. We have the pressure here already. So answer. First of all, I write the Bernoulli equation along the streamline that I've shown here. So this is the streamline that I've already drawn here between point 1 and 2. So along streamline 1, 2, 3, which is shown here, okay, I write the Bernoulli equation. So the Bernoulli equation is going to be P1, the pressure form of that, P1 plus 1/2 of rho V1 square plus rho GZ1 equals to P2 plus 1/2 rho V2 square plus rho GZ2, and this equals to, because they are all in the same streamline, to the this quantity is going to be constant along this streamline, so I can also write it for P3. For position 3 or location 3, it's going to be P3 plus 1/2 rho V3 square plus rho GZ3. Okay. From the configuration shown in the figure, I can say that Z1 equals to Z2 equals to Z3. Okay. This is the first thing I can say. And again, because here we have a large tank, again, the velocity here is, the velocity of V1 is going to be much smaller than V2 and V3, because of V1 is large tank. And you can also look at our previous examples that we had it before, like here, this one, right? When you have this much difference in the area between 2 points, you can write a continuity equation between those two. And so because A1 is much greater than A2, then V1 is going to be smaller, much smaller than V2, right? So the same thing here. And so I can say that V1 is almost 0. I can just neglect that compared to the other terms. Let me see if I can get it back here. So now let's see. So it's gonna be around 0. And also because I have the gauge pressure here, okay, I have, the problem gives me the gauge pressure, right? So the pressure that I want to write here is gonna be the gauge pressure. So that means that the atmospheric pressure is assumed to be 0 here. And because here we are at P3 here, we are in the vicinity of the atmosphere, right? So here we have the atmosphere, the free atmosphere here, free atmosphere. So the pressure at P3 is going to be equal to atmospheric pressure, and we can assume, because it's the gauge pressure, we are calculating gauge pressure, it's going to be 0. So it's free jet. Okay, so now we just plug in all these info that we have from the configuration of the problem into the Bernoulli equation. Okay. So the first thing is first I'm gonna cancel out all the z's, right, because they are all equal to each other. And then the other one is P3 is going to be 0, so I just set it to 0. And V1 is going to be also 0, so I just set it to 0. And so the first equation that I get is P1 equals to 1/2 rho V3 square, or V3 equals to square root of 2P1 over rho. Okay? And then the second equation, this is the equality between these two. And then I have another equation, which I'm going to write based on these two equations. Okay? So the second equation is P2 equals to P1, and then I take this to the left hand side, minus 1/2 of rho V2 square. Okay? And so this is air, and I don't know the density of air, but the problem gives us the temperature of air, the air temperature, right? So we can calculate the density of air using the ideal gas law, right? So ideal gas law, I write the ideal gas law to find this density here, density of air. So rho air equals to P1 here over RT1, right? The T of air here is also given. So it's gonna be, what is P1? P1 is 3 kilopascal. So I'm just gonna write it down. And this should be, you just note that this should be the absolute pressure. So in the ideal gas law, this is P1 absolute, right? And here I have the gauge pressure, P1 gauge, right? So I have to add the atmospheric pressure to get the absolute pressure here, right? So in theory, it would be the 3 kilopascal that I have from here plus the reference pressure, the atmospheric pressure, which is 101 kilopascal, right? So this is the P0 or P atmosphere, right? And then times, because this is a kilopascal, so times 10 to the 3 Pascal or Newton per meter square over R, which is a constant, gas constant, which is going to be 286.9 Newton meter over kilogram Kelvin times, and this T1 in the ideal gas law should be Kelvin. So I just add 15 degrees Celsius that we have plus 273 Kelvin to get Kelvin. And if you calculate this, this is going to give us 1.26 kilogram per meter cube. So this is the density of air here. Okay. So now I have almost everything, and I can get V3 from here because I have P1 and also rho. So let's just plug it into our equation. So V3 is going to be square root of 2 times P1. P1 is 3 kilopascal. So it's going to be 2 times 3 times 10 to the 3 Newton per meter square over rho of air, which we calculated here. It's going to be 1.26 kilogram per meter cube. All of these are in SI, and you should be careful that they should be written in SI to get the correct number unit at the end. And if you calculate this, this is going to give us 69 meter per second. Okay, so I have the V here. I know what is V here, and I can calculate Q. And Q is going to be constant, right, along this Q2 and Q3, right, because of continuity equation. So it doesn't matter if I calculate Q2 or Q3, they are going to be equal because if I assume that the density of this air is constant, so the mass flow rate, and we know that because of continuity, the mass continuity, how much mass is going here should come out. So the mass flow rate should be constant, and if density is constant, the volume flow rate, or Q, or the discharge, should also be constant, okay? So Q is going to be A3 V3, which here is, for this one, is a diameter, is a circle. So, and we have the diameter, so it's going to be, the area of that is going to be P pi over 4 of D square times V3, which is going to give me P pi over 4 of D, which is 0.01 meter. So 0.01 meter square times V3, which is 69 meter per second. And this is going to give me 0.0054 for 542 meter cube per second. Okay, so this is the flow rate that the problem wants, and then the second thing it wants is the pressure in the hose, or P2. So let's see, finding P2, because P3 we know that it is going to be the atmospheric pressure, and if in terms of gauge pressure it's going to be 0. So let's see, finding P2. From continuity we know that A2 V2 equals to from continuity we know that Q at 2 it should equal to Q at 3, or A2 V2 should equal to A3 V3, and so I know that A is gonna be here PD squared over 4. So let's just calculate that and see what is gonna be V2. So A2 V2 should equal to A3 V3. So V2 is gonna be A3 over A2 times V3, which equals to A3 to A2 is gonna be small d to big D square. So d small d or big D square times V3, and this gives me 0.01 meter over 0.03 meter square times 69 meter per second, which gives me 7.67 meter per second. Okay, so first I got V2. Okay, and now that I have V2, I can put it into this equation to get P2. Okay, so P2 is gonna be from this equation here, I just write it down here, equals to P1, which is, we know from the here is 3 kilopascal. So it's gonna be 3 times 10 to the 3 Newton per meter square minus 1/2 of raw air, which we know is 1 point from here 26 kilogram per meter cube times V2 square, which is this one, 7.67 meter per second square, which is gonna be, if you calculate it, 2,963 Newton per meter square. Okay. So this is one example for that we use both Bernoulli equation and continuity equation and also ideal gas law. Okay. So now let's go to another example and solve another example. So in this example, we want to determine the manometer reading in terms of Q, A1, A2, and S. Okay, so here this is the problem configuration. Okay, so here we have kind of a fluid, for example, water, that flows here and then goes from this side to this side. Okay, and then we want to find the manometer reading, and this is we have added a manometer here. Okay, and we want to see what would be this edge that the manometer reads. Okay, so if you just, for example, put this manometer into this system, you will see a height, a depth of this fluid that is here with that has a specific gravity of gamma water times S, right? So S is could be anything. For example, if this is mercury, this S is, for example, around 10, right? It's much larger than that. I don't know the exact number. I just say it. But the specific gravity, for example, of mercury is much larger because its density is much larger than water. And so we just show that the specific gravity of that with gamma water times S. And then here, this profile has a bigger d, and this one has a smaller d. And also this is inclined with respect to so the gravity force is not completely like vertical. So we have also a horizontal component here. So the gravity force is vertical, but I mean the flow direction is not completely vertical or also horizontal. It has both. It has a both horizontal and a vertical direction. So we have to account for that as well. And so let's get started and see how we can find this edge, which is the manometer reading, in terms of all these flow variables and also the geometry of that, which is A1 and A2. Okay? So the first thing I do is I write the Bernoulli equation along streamline 1 and 2. Okay, so along this line we have a streamline, right? So the fluid flow flows between these two. So I just write the Bernoulli equation between them. So P1 plus 1/2 rho. So this is the answer. Rho V1 square plus gamma Z1, specific gravity of water. So I just write it gamma water Z1. And then I have P2 plus 1/2 rho V2 square plus gamma water Z2. Okay? And then the other equation I write is continuity. So continuity between 1 and 2. So the continuity equation indicates Q, the flow rate, the volume flow rate. Because the density is constant, I can just write the volume flow rate. Q is constant between these two. So A1 V1 equals to A2 V2. Okay. And then I combine these two. So combine these two equations. And I get P1 minus P2 equals to gamma Z1 minus Z2 plus 1/2 rho instead of V1 square. I just use this formula. So here I can get V1 is A2 over A1 V2. So rho V2 square, I have 1 minus A2 over A1 square. Okay. So I have combined these two. So I have this A1 over A2, V2 and Z1 and Z2. Okay. So in order to find the manometer reading, what I want to do is to use the manometer rule, okay? Because this is a manometer, I want to use the manometer rule and go through between P1 and P2 to find another equation for the manometer, right? So I'm going to go, this is from previous chapter, so we are going to go from here, 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 here to get the pressure difference between point 1 and point 2, and then we have another equation from Bernoulli here that we can combine that with to get H, our manometer reading, okay? So manometer rule so I'm gonna start from point 1, okay? And then from point 1, what I'm gonna do, I'm gonna go from here to here, okay? So when I go here, what is this? This is, so if you have a vertical coordinate system, say this is a vertical coordinate system that I start here. Z, okay? So this much is gonna be Z1, and this much from here to here is Z2, right? So this, how much I've gone from here to here, let me show it with another color. From here to here, this much is gonna be Z2 minus Z1, right? So effectively, I have gone Z2 minus Z1 to a lesser depth, right? In the fluid. Okay. So I have gone Z2 minus Z1 to a lesser depth. So that means that I have to decrease that much pressure from P1 to get the pressure at here, at this point, okay? So I have P1 minus gamma water times Z2 minus Z1, and then I will get the pressure at here. This is based on the manometer rule, okay? And then I go still up, so I go up here, up to this point. Up to this point, this is given, so this is L. Not given, I just write it as L, okay? Not, it might not be really given. So I just write this as L, a length scale, or length I don't know, okay? And then, because I've gone to, again, a lesser depth, so I have to, again, subtract it from the remaining pressure. So it's going to be gamma water, L, and the length L that I don't know what is that, okay? And then I go this much again up from here to this point. And how much is at H, right? So I go like H meter or H foot, whatever the unit is, and I go again to a lesser depth, so I should again subtract that, so it's going to be minus gamma WH. And from here to here, from this point to this point, my vertical direction does not change. So the pressure from here to here is the same because from this coordinate system, only the vertical, the depth of the flow matters. And I have not changed the depth of the flow between here and here has not changed. So I am not gonna change, I'm not gonna add anything to my equation. And from this point to this point, I am going to a greater depth. So I have to add pressure to my current pressure. That is this point, right? And now I am in a different fluid, and you see it here, right? I am in a different fluid. It's not water. It's a manometer fluid, which has a specific gravity of gamma water times S, okay? So I have to consider that when I write it down. So I write gamma water times S times H, okay? And then from this point to this point, okay, it doesn't matter how you go, how much you go horizontal in the flow, right? We know the hydrostatic pressure is not a function of horizontal distance. It's a function, only a function of depth, right? So it doesn't matter if you, how much you go in the x direction. Is the only thing that matters is how much your elevation is changed in the z direction, okay? And you see from here to here, how much is it changed? Elevation, it's L, right? And I'm going to a greater depth, so I have to add gamma water L to my system, okay? And here I get to pressure 2 or P2, okay? So this is simply how you can use the manometer rule, which is a very useful way of doing it. And you see it's very simple and it's very powerful. We were able to add another equation between point 1 and 2 to find the pressure difference between them, okay? And so an interesting thing is that we didn't know L here, but this L, as you see here, cancels out, right? We have one term here. So let me show it. One term here, gamma WL, and also another term here. So these two are going to cancel out. And so I have another equation based on the manometer rule for P1 minus P2, which equals to gamma water Z2 minus Z1 plus gamma water H1 minus S. So I take these to the right hand side. Okay. So I think here I have made a mistake, small mistake that I need to correct. So this one is Z2 minus Z1. Excuse me for that. If you combine it, it would be like this. And so if you look at these two equations, okay, if you combine 1 and 2, we will get, so these all are equal, right? This one with this one is going to cancel out, and this one with this one is going to cancel out, okay? And so we are only left with these two terms. So 1 minus S times gamma WH equals to 1/2 of rho V2 square 1 minus A2 over A1 square. Okay. And since V2 equals to Q over A2, I can write this H equals to, from this equation, Q over A2 square, which is this V2 square, times one minus A2 over A1 square, which is this term, over two and gamma water is what? Is rho water G. So, or rho G, I just write it rho G because this is the same fluid. And these two are going to cancel out, so I'm only left with G here, 2 from here, and G from here, and then 1 minus S also should go here. Okay, so this is the formula of H, which is the manometer reading in terms of Q, A2, A1, and S. And this is what the problem wanted us to solve. So in this kind of problems, if you have a manometer, you make sure that you need to use the manometer rule to make your life easier. And so that will give you the hydrostatic pressure force formulas from the previous chapter, and also use that along with Bernoulli equation and continuity. So you will have 3 equations, and then you combine these 3 equations together, which is this one, the Bernoulli. So let me show Bernoulli, continuity, and manometer rule. You will combine these 3 together to get this kind of like the final thing that the question wants, either the manometer reading or other parameters that is thought to be solved. Okay. So this was the last example of this chapter, and now I want to introduce some important physical, I would say, applications of this Bernoulli equation that we are used for especially engineering designs to solve some examples and some problems. Okay, one of them is slice gate, which is shown here. Okay, so here we have a slice gate that is, for example, we have like a dam or something, or even it could be an open channel flow. We have some water, so we have some water here, and then the water, the gate at the top of this water, is kind of moved upward, and then the water kind of is released from the bottom surface, okay, from over the surface. Okay, so this gate is, for example, at the beginning is here, and then we just kind of move it a little bit upward, and so the water moves from here to the downstream, right? So it moves from the upstream to the downstream. And now what I want to do is I want to use this Bernoulli equation for this to find the flow rate at the downstream. Okay, so what's going to be the flow rate at the downstream based on a function of Z1 and Z2, right? And yeah, and also the width of this channel, right? So I want to see what is going to be Q based on Z1, Z2, and B. Okay, this is, for example, engineering design. Say you want to know what is going to be the flow rate downstream if you have, and you want to design like a slice gate width so that you can have a specific amount of water to be kind of go out of this system. Okay, so a simple way of doing that is using Bernoulli equation. So I write and apply Bernoulli along free surface 1 and 2. So along this one and this point, I applied Bernoulli. And why I can do that? The reason is I can have a streamline that goes from here and then goes here, right? So I have one streamline that goes this way. So I can write Bernoulli between these 2 points, okay? So let's do that. So we have P1 plus 1/2 rho V1 square plus rho GZ1 equals to P2 plus 1/2 rho V2 square plus rho GZ2. Okay? And then the second thing, I write the continuity equation between, so continuity between one and two. So Q is A1 V1, which equals to we don't know, so the width of it is here, right, in this direction. Okay, so we want to see what should be the width of this slice gate. Okay, so this is the width. It's a 2D problem. So this is B and this is Z1 minus Z2. Okay, so the area is gonna be at of A1 is gonna be B times Z1, right? So the area here this is Z1 and this is B. So the area here is gonna be B times Z1 times V1 equals to A2 V2, which equals to BZ2 times V2. Okay, the same width. Okay, and because I have written this on purpose between surface 1, 2, and 2, between point 1 and 2. I've written the Bernoulli equation on purpose because it's free surface. Okay, and so it's free surface. It means it's in the vicinity of the atmosphere. So the pressure at point 1 and 2 is gonna be atmospheric pressure. And if I write P and P2 based on the gauge pressure, I can assume that they are 0. Okay, as if they are written as a gauge pressure. Okay, so these are gonna be 0. And so I can write 1/2 of rho V1 square plus rho GZ1 equals to 1/2 rho V2 square plus rho GZ2. Okay, and rho's are going to cancel out in all the equations. They are equal to each other. And so what I'm gonna get is V1 square over 2 minus, instead of V2 square, I'm gonna bring this to the left hand side. Instead of V2, I'm gonna write based on this, V2 equals to Z1 over Z2 of V1. So I just write it down. It's gonna be Z1 over Z2 square times V1 square over 2 equals to G Z2 minus Z1. Okay? So I use both. In here I have combined them with continuity. And so let me rearrange the terms. If you rearrange them, you're going to get V1 square times 1 minus Z1 over Z2 square is going to be 2G Z2 minus Z1. Okay? So the flow rate, what is going to be the flow rate? The flow rate that we want to find is for this slice gate is going to be Q equals to BZ1 V1 from here, right? Which is going to be BZ1 square root of, from this equation, 2G Z2 minus Z1 over 1 minus Z1 over Z2 square. Okay? Also, this equals to, if I want to write it in terms of the second velocity, Z2 BZ2, right, based on this one, it's gonna be BZ2. And if you again calculate that, you are gonna get for V1, for V2, which is gonna be Z1 over Z2, you're gonna get this formula. 2G Z2 minus Z1 over 1 minus Z2 over Z1 square. Okay? So if we assume that Z1 is much greater than Z2, that means this slice gate, the depth of this water before the slice gate is much larger than how much we kind of open that, this Z1. So we slightly open it, not too much. Then we can assume that this term here is gonna be 0, right? If we assume that, if we assume this, then Z2 over Z1 is gonna be about 0. Right? And I think I have written, I made a small mistake here. So this should be Z1 minus Z2. Okay. Yes. And also Z1 minus Z2 is going to be about Z1, right? So I can use this, and this will give me Q is BZ2 times square root of 2G, with this approximation, 2GZ1. This is an important approximation that we found from continuity and Bernoulli equation, applying Bernoulli equation for this slice gate problem. So we found that the flow rate here is a function of width. So if your width is larger, your flow rate is going to be larger, and also Z2 and Z1. And it's linearly related to Z2, but it's not linearly related to Z1. So it's kind of increases as square root of Z1, right? So this is the flow rate that we found by using this approximation and applying Bernoulli equation and continuity. Okay, so this one is just Z1 minus Z2, and this one I just assume it is almost this one is about 0 because of this, and so this one is just going to be 1, right? The denominator is going to be about 1. Okay. So finally, the last application I want to mention for these kind of, I would say, hydraulic structures that can be used is what we call, also we come back to this in the open channel flow later on with more details, but this is called crested weir. So we have a plate here, wear plate, and so this is from the front view, and this is from side view. So we have some water that goes from here to here, okay? And then this is the plate, this plate that we have. And then we want to see what is going to be the flow rate above this crested weir, okay? So we want to know what is the Q here. How much mass flow rate we have here, and these are very important for the designs, right? You want to design like a structure, and then a hydraulic structure, and you want to know how much mass flow rate you are going to have, okay? So this is something that is approximated, also can be similarly approximated using Bernoulli equation, and I just write it down. So Q is going to be C1 H times B square root of 2GH. You see the similarity here. And here we have H, which equals to C1B square root of 2G H to power 3 half. Okay, so let me explain what it is. So HB is what? Is just area, right? Okay. HB is just the area. And C1 is kind of a constant depending to kind of correct this, because this is kind of an empirical formula. And so H times B, and then we have this square root of 2GH, again similar to this one, okay? And so this C1 is a constant to be known. And this is kind of an empirical constant, depends on the shape of this weir, right? So for example, if you have a complete rectangle, it's going to be something. If you have like a triangular weir, it's going to be something else. So, or circular one. So these are all going to be different. Okay, so it's a constant to be known. And so, but the thing is, you can see for this kind of problems, Q is going to be approximately varies as h to the power 3/2. Okay, for the crested wave. Okay, and you can get this again with this Bernoulli equation and similar approach that we use for slice gates. Okay, so let me briefly review what we learned today, and this is the end of chapter 3. So then in the next lecture we are going to go to chapter 4. So first I solved an example for determining the flow rate and the pressure in a hose. So we had this problem. So we applied the Bernoulli equation along point 1, 2, and 3 because this was along one streamline. And then again we assume that V1 in the tank is much smaller than V2 and V3. So V1 is around 0, and P3 is 0 because we are in the free atmosphere. And using this, we wrote the Bernoulli equation. And then we also used the ideal gas law to find the density of air, which was not given. Only we had the temperature of air that was given to us. And so using these two, we were able to find the Q, the flow rate, and also P we found P2 using the continuity equation between point 2 and point 3. Okay. In the next example, we had this manometer and we wanted to see what would be the reading of this manometer edge. So again, we used Bernoulli equation between point 1 and 2. This gave us one relation. And then we used the continuity equation between point 1 and 2, and this gave us the second equation that we needed. And finally, we needed one more equation to find these edge in terms of Q, A1, A2, and S. And that was the manometer rule that we use, or we can use the hydrostatic pressure formulas. So we started from point 1 and went to point 2 using the manometer rule, and then found the third equation, and we combine all this equation together to find the manometer reading based on those mentioned variables. And finally, we use this Bernoulli equation. We can use it in some real hydraulic structures to find the flow rate, mass flow rate or volume flow rate. And we use that for slice gate as an example. So we apply Bernoulli equation between point 1 and 2. And then we combine it with continuity equation. And then we found the flow rate that is coming out of this slice gate as shown here. And finally, for the crested weir, we said that we can use a similar approach, and this is kind of an empirical formula. And we showed that Q is varying as h to the power 3/2 for these crested weirs. Okay. So this is kind of the end of this chapter for Bernoulli equation, and then in the next lecture I'm going to go and introduce the Reynolds transport theorem, and after that we are gonna go through the momentum equation in fluids to find the force in different structures, hydraulic structures. Thank you very much, everyone.